Hello everyone and welcome to another lecture. Today we will be seeing some examples of vector space. In our past lecture we gave the definitions and we tried to motivate why we need a vector space. We saw that there are several properties of the vector space, and today we are going to see through some examples how we can identify vector spaces. That is, given a set of objects, can we find out whether they form a vector space or not. So the first thing we need to consider today is that let's say our example 1 So we want to take the space consisting the set of arrows that we are familiar from our course on introductory physics and vector analysis. So any vector in this subset, that is, if you have a xy plane, let's say, and the objects that live here, these arrows, they can be in general represented as, let's say I want to denote it as v, and there is some a, it's a number, and it's an I hat, and b, it's a j hat. I want to express these vectors like this, and I can take another vector denoting by w, and let's say it's c I dj. Now we need to check the conditions, that is whether v plus w belongs to this space as well. This is the thing we need to check. So here is the check. If we add these things, those components will add up, and you can see that this a plus c is something new. By new I mean if you could take a equals to 1, c equals to 2, and this will give you a 3, that is a real number. Similarly for d plus b. Now notice that these elements are in the real number, and this space, that is this xy plane, will actually have a field of r squared. That is, you have one set of real numbers in the x-axis and one set of real number in the y-axis, and when you add them, the resulting vector also lies in the same space. That is, this a plus c also lies in the field r square, and d plus b also lies in the field r square, and as a result this whole thing also lies in this vector space. So the first one is checked, that is, the first property is checked. What about the second one? The second one is pretty easy. The second one, let's take any k that belongs to r square, and if you multiply k with v, this also belongs to the vector space xy. That is our xy plane. Because let's take a vector like this, and whenever you scalar multiply, depending on whether it's a positive scalar or a negative scalar, if it's a negative scalar, it will just get oriented like this, and then if you multiply this with a positive scalar, it will just scale up. That's it. But notice the subtle fact that we are considering x, y, and here we have minus y and minus x. So we're considering this whole xy plane. If we had taken only the x, y, where let's say x can be both positive and negative, but y can just only be positive, that wouldn't form a vector space. Because if you recall that one of the features of the vector space was that a vector space should have something called a zero vector, and if we had only taken this xy and minus x, only this region, we could never make a vector that lies in the xy plane like this, let's say 2i 3j or minus 2i 3j, whatever you want to take. We could never a vector like this into 0. So that's why it wouldn't make a vector space. So since we have only considered these two properties for this example, but it is also essential that you check the other properties as well. And for this xy plane, the other properties will be satisfied as well. So let's now take another example. Let's call this example 2. So today I'm just only gonna be discussing examples, and now we want to take something a bit crazy. That is that we want to take set of all 2 by 2 matrices, and now we want to check whether they form a vector space or not. So let's switch to another color. So any 2 by 2 matrix will have a following form, where these entries can be in general complex. So again, if nothing is specified, it's better to take the elements to be a part of the complex field. And let's move on from here. You can see that any matrix, let's say I'm calling this matrix A1, and this will be a part of a vector space, and let's call it A, B, C, D. And take another matrix A2, let's call it E, F, G, H. If I add them, this is just A plus E, B plus F, C plus G, H plus D. So as you can see, this whole thing also belongs to that vector space of 2 cross 2 matrices. I mean, this 2 cross 2 matrix, the set of 2 cross 2 matrices will form a vector space like this. And the reason I'm saying this without changing the second property is that from our earlier discussion from week 1, that we saw if I have a scalar, let's say small s, and there is a matrix, this just means that you have to multiply this scalar with all the elements of this matrix. And for this case, if you do that, the elements will also belong to the same field, and as a result we will get another matrix that is also on the set of 2 cross 2 matrices, and it will satisfy all the other 8 properties as well. So the reason this example of matrices is interesting, in a sense that it's interesting because here we have no notion of magnitude. Let me just use another color so that you understand it better. Let's say magnitude and direction, because those are matrices, right? So how can you get some magnitude and direction from a matrix? So that's the abstractness of that we're talking about, that we want to generalize stuffs. So this is what it becomes, that here you can see that the structure of this matrices and the structures of these two-dimensional vectors that you know from introductory physics, they look alike. The structures are alike. But yes, even this is a bit disclaimer that yes, in fact you can introduce a notion of distance for matrices as well, something called a trace norm, but it will be discussed later, hopefully, in this course. And the very notion of distance actually arises from something called an inner product, and we will see that later. But let's now focus on another example. So example 3. This example 3 will be taken as follows. Let's call this the positive z-axis. Again, we are back to our ordinary three-dimensional space. Let's call this the x-axis. Opposite to this is minus x, and let's call this the y-axis, and opposite to this is the minus y-axis. And any vector over here has a component in the z-axis, in the y-axis, and on the x-axis, right? I mean like this, though the drawing is not pretty accurate. But here notice that we haven't drawn the minus z-axis. So if I want to show that this does not form a vector space, and all we need to do is we need to find one counter example. That is, when you want to prove something in mathematics, you have to go through all the axioms and you need to check that all these properties are satisfied. But when you want to disprove something, only one counter example is enough. So let's take a counter example. Let's call a vector v1, write it as 2i plus 3j plus 5k. And we said that for every vector space there should be a zero vector, and for that to happen we need to have something called a minus v1, right? And it turns out that this minus v1 is just minus v of 1. And if you do that, that is, if you say this guy belongs to the space, that is the 3D space, with only z plus, that is the positive z-axis, you can see that this is wrong, because when you do this minus v1 you get minus 2i, that is over here, minus 2i, minus 3j, minus 5k, right? But minus 5k doesn't exist. We didn't start with minus 5k, we never started with the minus z-axis. So this shows that the space we are considering is actually not a vector space. So this is how you can easily find counter examples, but you have to be a bit tricky over here. And this counter examples proves that 3D space, also sometimes written as like this, but let's just ignore that. We'll only let 3D space with z-axis plus. Don't confuse it with the set of positive integers, because sometimes z plus is used to denote the set of positive integers. So that is z-axis with only plus direction or positive direction, does not form a vector space. And the last example for today will be something similar to we saw in lecture 1. And here we want to be a bit more explicit. We want to take two functions, f of x and g of x, which is defined over the interval, let's say 0 to L, where L is some number. And let's say you have a graph of, let's say this is 0, right? And this is, okay, let me use another color. This is 0, this is L. And let's take the graph of f of x to be in the green color, let's say like this. This is the graph of f of x. And the graph of g of x, let's say it goes something like this on this specific interval. And we are assuming these are continuous functions. There is no discontinuity and all that. Now, if you add them, let's say I want to add this g of x plus f of x. The resulting function will also be continuous in this range. I mean in this interval, sorry, not range but interval. So let me choose another color to fill it in. Let's say I want to fill it like this. This is obviously not an actual representation, but this addition is defined over the same interval when the addition at point x is defined. That is, we are actually doing a pointwise addition. So, and in this case, our identity, because remember, two of the crucial things that we discussed was that there should be a zero vector like this, such that when you add it with another vector, it gives you the same vector. For our case, we have a function f of x and g of x, and in both cases the zero function, that is if you consider these functions as vectors, the zeroth vector is nothing but the zero function. That is the function, let's say call it f prime, or I don't know, f tilde, and this is always 0. This is the additive identity, and the inverse is just minus f of x. So that f of x minus f of x, sorry, plus, okay, let me erase that. So that is f of x plus minus f of x is equals to 0. So this is how we can see that even this function, the functions we deal with, they are also forming a vector space. So that's why in the earlier lecture and even in this lecture we said that these arrows that we see in vector analysis, and even for a far more different thing, these functions, they possess a similar structure when we think in terms of vector space. And I hope this example video was enjoyable, and thank you. I'll see you guys on the next lecture.